made a team here, one after the other each day. We just flipped orders this time, so theory and experiment. But I'm also going to flip topics a little bit. But both of us have made the same decision, and that is to go and look at an application of what we've been doing. And so I'm going to talk some about applications, but within the same context of everything I've been talking about so far. So I will still use the generation of high harmonics as the underlying problem. So I'm going to cover three things. I'm going to cover orbital tomography. And I left you hanging about the issue about this. I'm going to come back and just remind you of where I left off last time to begin with. Then I'm going to move from there to photochemical dynamics and show you how you can apply these really broadband pulses to advantage in looking at photochemical dynamics. And then finally, I'm going to address, is there any chance of doing anything interesting in condensed phase? Of course, I wouldn't do this if I wasn't going to answer it yes. So you know the answer to the question that I put up there. Now, I put this figure up very close to the end of my last talk. And I want you to look at it for a minute. This is an interferometer. If I make this a spectrograph there, and I put an image of a spectrum, actually I took it from a photoelectron spectrum, but it's a spectrum as a function of time delay. If I make it, that's a frog setup, and I think the first lecture I told you that we can measure E as a function of t, amplitude and phase, all aspects of the pulse, using a frog setup, which is an interferometer, a nonlinear interferometer. I didn't show you, but I think you would accept if we could do it E as a function of t, we could do E as a function of x, but in space, and in fact that's true. So we can take a pulse and characterize it completely, amplitude and phase, from only the amplitude information that you have in hand. So the challenge is, can we make similar measurements of, well, the thing that's involved in this, molecular orbitals or molecular wave functions, and molecular dynamics, and actually, in fact, attosecond pulses that are being formed, because they're also being formed in an interferometer-like way. Let me now jump to the interferometer that underlies attosecond generation. You've seen this image before. There's a wave function, a wave packet that's pulled out, comes back, and there's an interference between the wave packet and the wave function. An interferometer made by light, but an equally precise interferometer to the interferometer we're used to with ordinary light. It's precise in the sense that we can move the arms of the interferometer. We can move the arms of the interferometer by adding a second color, polarized parallel. Actually, you've heard this a few places now here. People haven't described it always in this terms, but you've heard about adding another color and the advantage that can be. You could also bring it in at a different angle, and you've heard me talk a little bit about coming in at a different angle, and you make a grating. You could also come in with a different polarization and bring the electron in at a different angle. There's all kinds of ways you can manipulate this underlying interferometer that's below high harmonic generation. Here I want to also add something else. Instead of having just a simple atom like a hydrogen atom that's been applied, we could replace that with a molecule, a nitrogen molecule, for example, and that's what I'm going to do in a minute, or a bromine molecule. I'm going to do in a few minutes more. And that molecule we could choose to align in some different way. I show you an angular distribution of alignments. I'll show you in a few minutes how I get that. And you could imagine moving that, and in other words, removing the wave function from which we start. And in some sense, that's moving the arms of the interferometer as well. And so we can do all of those things. And so we should be able to set up, and I talk about how the interference and how you measure that interference. So you recognize this figure. These three figures are all So the radiation that we observe is reading that interferometer as it is generating high harmonics or attosecond pulses that we've talked about everywhere else. I want to go back again and emphasize how it's reading it. It's reading it through the transition moment or the dipole moment. The dipole moment is what's induced by the interference, and that dipole moment in the strong field approximation. That's the approximation that once the electron is free, you can ignore the Coulomb potential. The dipole moment in that approximation is the integral of the wave function times r times the recollision electron wave back at e to the I kx, now assumed a plane wave, coming back again, e to the I omega t, and then some amplitude to represent the amplitude at each k. In some sense, the only uncertainty here is the wave function from which it came, you might say. You could imagine the plane wave, we know, we can measure it. We measure the frequencies for sure, and we can induce the plane wave with the k vector. And the amplitude could be measured in some other way. Okay, so now I want to go on and leave you exactly where I left at the end, and you've probably been thinking about it. And so, where do you stand on measuring molecular orbital wave functions? So, some say that orbitals are intrinsically unmeasurable. Let me repeat why they say it. They say there is no such thing as any electron going around in an orbital. Electrons, there are many electrons in any system in which we're talking about, like a nitrogen molecule. All these electrons are identical. They're interchanging with each other all the time. There is no such thing as an electron in an orbital, and therefore, it's a mathematical construction, the argument goes. It isn't real. You can't expect to think of an electron in this orbital, and of course it's unmeasurable. And I think chemists are taught that. I really do. I think this is a natural thing that everybody is taught. I think less clearly people say you can't measure a wave function, or probably there are ways, I think. But it's, I think chemists had felt quite strongly that you can't measure orbitals. So I don't know what you think about it. I said, think about it before you go. I want to talk about the experiment. So I'm going to show you an experiment. I'm going to give you the arguments for why it works. And I'm going to show you the degree to which we can say something about the orbital, and even talk about the kind of orbital that we measure. Okay. So, I'm going to start on it. It's going to be molecules now. You've heard a little bit about molecules from Lars Madsen in his talk earlier. And you even heard a little bit about alignment. I want to just briefly say how it works. So maybe I'll repeat what he said before, but I'm only going to say it very briefly. He said it much better and much longer. Imagine you have a jet of gases. Think of those as the nitrogen, jet of molecules. Think of those as nitrogen molecules. That's what we're going to use for now. Let's imagine we bring a beam of light into that, linearly polarized, whose intensity is strong but not ionizing. Up to but not over the ionization. Up to but not over. This induces dipole moments inside the system. The dipole moment interacts with the field, causing a torque towards an alignment or a potential well in some directions of alignment for the molecule. Think of the molecule like this. Think of the laser field as along here. The electrons can be biased to one side or to the other side, depending on how the field is going. The dipole, thereby induced, interacts with the field, and that's the polarizability, and there's a star shift associated with it. And molecules are pulled towards an alignment by that strong laser field, and you can see what they would look like after they've moved to the middle of the potential of such a field. Since this pulse that we interact with it is short, we can choose the pulse length so that the molecules see this potential well, fall into it, and we turn it off right at the end of it. It's a bit like a pendular problem. Think of all kinds of pendula sticking here. Imagine there's no gravity. We turn it on, they all start towards the ground, and then we turn off gravity when they get close to the ground. And anything within these small angles that allow them all to come together, like in a pendulum, will be aligned, and that's what happens in this. It's really a pendulum problem. Now we have the molecules aligned, and of course, molecules have a spectrum, a rotational spectrum, that leads to periodic realignment, periodic structure of how this rotational wave packet evolves. So if we do an experiment with a pump pulse that comes in whose purpose is to align a molecule, we can come at any other delay afterwards, knowing how the rotational wave packet evolves, and interact with that pulse, creating harmonics and probing it thereby. And that's the experiment. You understand the experiment, and you understand, hopefully, qualitatively, the alignment process. Stop me if you wish anywhere like before. Okay, so how well can we do this? This was some time ago that we did. We could probably do considerably better now. How well we can do this? You saw this one. I just took it up in one of the earlier slides to show this is a Coulomb explosion image of the nitrogen molecule. We've gone rotationally aligned it, waited until it got to as best alignment we can get. We come with an intense pulse. We pull off a whole set of electrons simultaneously. And we look at the ions as they fly apart by their Coulomb repulsion so fast that they can no longer move anything except repel each other. This process, in this case, we look at nitrogen 3 plus and 2 plus, I believe it is, making it a full 5 plus for the ion, overcoming, we hope, all bonding or dominating all bonding that's left in the molecule. This is a distribution of the probabilities of seeing fragments go in different directions. So small probability this way, large probability this way. The molecule is aligned with the distribution roughly as you see it. This is a 2D projection. By changing the polarization of the light, we can change the alignment of the molecule, and there's a whole set of, I think, 4, 6, 8, 16 of them. So that's the degree of an alignment we're going to use in the experiment I'm going to show you. This is done, actually we probably do a little better in the experiment I'm going to show you. This is done by an effusive jet of gas going into a vacuum chamber, very low density in this case, and then we explode the molecule. In the experiment I'm going to show you, we use a supersonic jet, so it may be a cooler distribution to start with, although we keep the density somewhat high in order to make harmonics so it isn't fully cold. Okay, now what's the concept now? We know how to align molecules. We know how whole idea of interference. I think the concept is caught here in an artistic rendition by somebody who wasn't a scientist. And so this is you have to think of it as a cartoon. And this is the cartoon version of the HOMO orbital of a nitrogen molecule, where blue and red represent the opposite phases of the wave function, arbitrarily labeled plus and minus. There's no plus and minus, of course. They're just arbitrary labels. And where the molecule is aligned in this image along the direction of the laser polarization. And this image is meant to show you the recollision electron wave packet coming back. You know that it chirps. The electron wavelength or energy in the beginning and the middle and the end differ. And caught here is the middle, and by the artistic way the artist has set it up, you can see that the wavelength is approximately the structure size of that orbital. Now you can think about interference, and I want you to think about it as I talk along. You can imagine what that interference might have looked like when the wavelength was longer than the structure size. It would be different. There would be modulations going on inside it as the wavelength moved around. Different kinds of modulation. Equally, it will be different when the wave packet becomes bluer. And so the radiation that we see will have to be different, of course. That's what we're seeing in a high harmonics. It's just words to tell you what you're seeing. Now think about taking this distribution, since now you know we can align the molecule and rotating it through 90 degrees. I don't have an image for that, but you can all think about interference, and think about the interference and how much different it must look if we have the molecule aligned like this when the wave packet goes back, or like this when the wave packet comes back. And all other alignments, you saw what we can do for alignment. Actually, that should make you think a little bit about tomography. I put a picture of a tomograph, medical tomography I pick off the internet, just to make you think about it. And that's the basic idea that's behind the molecular imaging of orbitals. So we said, okay, let's set up an experiment and look at high harmonic generation in this way. Let's look at high harmonic generation where we control the molecule with the degree of control I showed you. And that's done with a 2-pulse experiment then. We start out with a pump pulse. The pump pulse, in this case, is 60 femtoseconds in duration. Its intensity is 5 times 10 to the 13 watts per square centimeter. And it's focused from a relatively small beam coming into the target chamber, leading to a relatively large focus where the gas jet is formed. The gas comes out of a supersonic jet. We estimate the temperature to be somewhere on the order, but it's a pretty soft estimate, on the order of 20 degrees Kelvin. And the gas jet densities and length are quite short. I think the length is about 200 microns of the gas jet, and we work in a place where we don't make much harmonic conversion. The issue is not harmonic conversion, but to see the process. We want phase matching to play a minimum role in the process. The probe pulse, which is going to make high harmonic generation, must be more intense. Its intensity is 1.5 times 10 to the 14. Its duration is shorter, it's about 30 femtoseconds. And so it comes in and it's focused from a larger size outside and therefore to a smaller size inside, hoping to overcome and have uniformly illuminated sample, uniformly aligned sample in the center. The beam then, the harmonic beam is then brought out and picked up at a microchannel plate off of grating. And this is a typical harmonic spectrum that you see. It's actually, we go from, say, the 15th harmonic to around the 39th harmonic. In fact, we go a little further. In this case, you see the 39th harmonic. In other words, photon energy of 23 eV up to about 60, and actually slightly beyond. Now, it's not the wavelength of the light that's kind of important here, but it's the wavelength of the electron. So 100 eV, the wavelength of the electron is in the order of an angstrom. Okay, so the electron is doing the interference. So the underlying electron wavelength is in the order of an angstrom. Now I'm going to show you the data that we see. The data that we see is here. It's almost raw data. It's not quite. We have, as you remember from the transition moment, we have to know something about the amplitude of the wave packet coming back at each frequency. And so we either have to measure it or calibrate it out. What we choose to do is to calibrate it out by using an atom as a reference, an atom that is almost identical in its ionization properties to nitrogen. And that's argon. There's been many studies of argon versus nitrogen, and they ionize very similarly, aside from the details of ionization as a function of angle, and it's not very, that's not so strong. So we use argon as a reference. So what we see is the raw data here for nitrogen as a function of angle, where argon is used as a reference, but of course argon doesn't change as a function of angle. It's a constant reference. And we assume that we know the argon orbital in calculation, or in the experiment. So here's harmonic number again, plotted across here. I told you we go beyond harmonic 39. In fact, it's up to harmonic 43, and it starts with harmonic 17. There's 19 different projections here. I'm sure you don't want to look at each one. I think the only thing to look at is the very different and unusual structure of this and how it changes as a function of angle. You see a minimum in this region, and you see peaks in other regions. And so we use this data with the assumptions of polarization, which were then not measured, since they have been measured, and the assumptions we use are correct. An assumption that there's a phase jump here at the minimum that was then not measured and has been measured now, and our assumption was approximately correct. And using that, we put it into a tomographic algorithm to reconstruct the wave packet. The tomographic algorithm is just a tomographic algorithm that's been developed by others. It's nothing to do with us. We just put it in the algorithm. It assumes a plane wave coming back again, just like you would have in ordinary tomography, because light can be done that way. It assumes a plane wave coming back, and here's the reconstruction of the nitrogen orbital that comes from those 19 different projections, just directly out of the tomographic algorithm with the assumptions only that I mentioned. Here it is, so you see immediately the 3 lobes that you know are there in the wave function, and that was there in the artistic sketch. This is a 1 electron Hartree-Fock calculation of what it might look like. I think it's better to compare it with the following. This is a multi-electron calculation, a more sophisticated calculation of what the harmonic spectrum should be, but also filtered by the fact that the maximum energy of the electron coming back again corresponds to giving us a harmonic number of about 65 eV, what we have in the experiment. You can see that there's a great deal of similarity. Of course, we see the nodes where they should be no matter what. We see the 3 lobes where they should be. We see the basic structure where we should be for the multi-electron effect. We see halos around it experimentally. I'm sure those are not real, but of course we're making a plane wave approximation to an electron that's coming into a Coulomb potential and therefore is being distorted. And there's clearly errors that come in here. There's clearly errors that come in here. However, we get the amplitude and relative phase. It's the wave function, not the wave function squared. In other words, we know that the phase here and here are different. Of course, there's an absolute phase that we do not know. It does not make sense to even talk about. And so just like in optics, there's no absolute phase. There's no absolute phase here as well. So in that sense, otherwise we see the wave function, not the wave function squared. So this is the tomographic picture of the molecule. You might like to say, okay, what have we really measured? What kind of orbital? Because when you begin to look into it, there are multiple orbitals that chemists think of it one way and other people think of it another way. So let's place what we've heard all so far in a multi-electron language. The experiment makes, of course, I've said all the time, a superposition of it takes a wave packet and splits it in two. A wave function splits it in two, keeping a wave function and a wave packet in a continuum. Let me say it differently. We have the molecule intact. The n-electron wave function is one of the superposition. And we have a molecule in which we have n-1 electrons in the ion and 1 electron in the continuum. And that's the superposition. And we see the difference between the n and the n-1 electron wave function. It's the Dyson orbital. We look at the Dyson orbital, the difference between the n and the n-1 wave function of the molecule. Let me just say a few things about what you see. Since tunneling selects the initial state, we must return to the same state or to a state that is coherently related to this initial state. If it selects 2 or 3 states, then these 2 or 3 states you can return to by the electron wave packet. And that leads to interesting potentials for looking at dynamics that's launched by the process of tunneling, but I will not go there. I will not talk about that any further. So this is the orbital tomography that I set up for you in the first place. And you might want to look at it critically and say, okay, does it work? Is this real? And have we found a way to measure an orbital? Or maybe not exactly a chemist's orbital, but it looks like what they would have in all of their textbooks, really. I'm going to keep going if there's no other questions. I'm going to just make a jump now to electrodynamics.
I don't really follow the argument that you haven't done what you've said you've done. I don't understand the argument why it shouldn't be able to be done. I don't understand the objection to your research that's presented. I feel like if I understood it better, then maybe I would be able to understand, you know, what, I feel like there's something that I'm missing that other people are objecting to.
In a way, I think maybe I overstate the objection. So let me comment on this a bit. What I said is correct as far as I know. The chemists are taught that orbitals are unmeasurable. And so when this paper came out, I spoke at Yale not long ago, and the professor said he was ready to give the exam. I mean, it was just right at the end of the term. And students, he saw this paper, and students began to ask him about it. He put a question on the exam about it. And they had huge discussions around at Yale about whether this was a measurement of the orbital or not. People from Dudley Hirschbach called me from Harvard and said, this is really amazing. They never thought an orbital could possibly be measured. And this will change how chemists are taught about orbitals in general. So, I mean, chemists have accepted this to a large extent, that this is a measurement of an orbital, although maybe slightly different orbital than the orbital they normally think about. It's a Dyson orbital, it's a well-defined orbital. So maybe I overstate that it's uncertain. However, I have given talks where people are very, very, very disturbed by even saying, did you think you can measure an orbital? I had a man that stood up at the end of the talk that I gave in Vancouver and said that this was just garbage science and it shouldn't be given. And he actually wrote to the president of the National Research Council where I worked at the time. I'm now at the University of Ottawa for not the same reason. And he said I should be fired. He said I should be fired. He did. The letter said I should be fired. But fortunately they didn't fire me.
Paul, if you could go to the next slide. My reservation is with point 2, okay, not with the experiment, just the theoretical aspect. So with an n-1 bound molecular orbitals and one continuum orbital, no theory can ever produce an exact wave function. It's always a matter of a representation, because I have an infinite number of continuum states which this extra electron occupies. Therefore, whether I can say that the theory can reproduce an exact wave function, I think it's here is not applicable. I'm only referring to the theory, not the experiment, of course. That's my concern.
I'm not sure if you're saying the same thing. I might say that it's not transparent here that we create a relaxed ion. We pull the electron out of the ion, and is it really
it's relaxed? A matter of representation.
Which is what would be the Dyson orbital. It's a relaxed ion versus the relaxed molecule.
Yeah, and then the theory would produce, upon a representation of these orbitals, a wave function. And another theory will produce another wave function, and so on and so forth. They can agree up to 16 significant digits in their bound state energies or the wave function energy, but they can never be the same. That's my point 1. I think it's I tend to agree. For N2, it's possible to produce an N electron bound wave, molecular wave function. That's mine.
There's another aspect that's come up. There's many aspects that have come up in the past, since this experiment came through, and people have worked on it to a certain extent. So we now know, which we didn't know then, that it's possible that when you ionize, you have a significant chance of pulling out an electron from a deeper level. Actually, Lars mentioned that earlier. I think it was you, maybe it was somebody else. I think it was you. So tunneling takes not only the top electron in a system, even maybe like nitrogen, for sure like nitrogen, but also deeper bound electrons. You might find that hard to accept because we all know that tunneling is exquisitely sensitive to the barrier height, and there's a significant difference in IP on the level of IP between, say, the HOMO, which is what we're measuring here, and the HOMO -1 of nitrogen. However, we're ionizing at an incredibly fast rate, even if the lower level becomes significant. And so it can play a role, and people have worried about how to separate these different orbitals, particularly the group in France, as done so. So there's been some extra work done on it, trying to deal with the real complexities of the system. We went on to look at dynamics, which I'm going to show you next time, but we didn't eventually try to do a movie of the orbital change. There's a number of questions, so I'm sort of stopping to stimulate questions, and I'll go back here.
I have two concerns. So first, when you say you measure the electron, you measure the function.
Excuse me?
You say you could measure the wave function. A wave function is not actual thing. It's more like a mathematical description, and you say you can represent it in such a way. Is that some contradiction?
I mean, I think there's also a good, so I argue you measure the wave. Of course, it's not one molecule in that measuring. You measure multiple molecules to get a harmonic. You would not get a harmonic spectrum from one molecule. You would get, if I made a measurement, so a harmonic would be some frequency, I guess. So I have a gas of atoms, and we try to make the phase matching as benign as possible. So this is an amplified version of the single atom response. We've done many experiments to confirm that, but it's not one of them. So maybe that's also, I should be careful about that. I think when you look at it, you have to think of it that way.
This is.
I got many people now. So of course I'll be very specific. I'm careful.
Yeah,
Right,
this is what I wanted to say. It's not really, what you have measured is not a single electron wave function. You've measured the density operator of a large ensemble of systems, which very, very carefully prepared in a way that it's essentially in a pure state, right? But it's always what tomography does, and I don't think that anybody would fire you for that. I would not.
But at least I have the phase. I do
Yeah,
have
yeah,
phase.
you have the space. But people
I have
like
phase.
Serge Haroche who does tomography of photons.
Yes.
It's kind of the same idea.
I think it. I agree.
Yeah,
I agree.
it's beautiful.
I don't see the problem in the sense that your measurement in this case is on harmonic generation. And you need, as someone back there said, you need some model
With you,
that relates
it was
the
at the
initial
second
state
point, it
to
wasn't,
what you measured the harmonic
and we
generation.
should do with your point.
And if you formulate things in such a way that you show the influence of the initial state on what's measured, in some sense, that's a description of the initial state.
So, I'll say what Hossein said. I don't have a problem with the experiment and the data. I think all the question is the interpretation stuff. And I think, frankly, part of the problem is you stated a little provocatively when you say you measure an orbital. If you came out and said I measure a Dyson orbital or something like that, I think probably there would be less issue, because Dyson orbitals have a clear definition,
Yeah, clear.
and it's an orbital, but not in the normal molecular orbital sense that you talk about a Hartree-Fock orbital. My problem with the statement that you measured an orbital is orbitals are unmeasurable. I will say that unequivocally if you're talking about a Hartree-Fock orbital. First of all, there's many reasons why, because that orbital is not a well-defined thing, first of all. Which approximation did you calculate the orbital in? Real systems are multi-configuration, so it's, which is fine in the Dyson orbital picture, but not by itself. And of course, you can always take unitary transformations among the set of orbitals in a single Slater determinant, and that's unchanged. So those orbitals aren't well-defined things. You made arbitrary choices, and we never measure arbitrary things. We never measure things with arbitrary choices. So, but I think measuring the wave function or any wave form is fine as long as you have a reference that you know, right? And I mean, that's what you've done here. You said you knew the plane wave coming back, right?
And it's phase related to what started.
Yeah, you're
That's
beating it
very
against a
important.
known wave function or against a known waveform. I mean, you do that to measure light fields too, right?
Right, I mean, I would agree with Fred. I mean, you have it because everyone would agree that there is a wave function for the molecule. We'd all agree that we don't know it, but we would all agree that up to an arbitrary phase it exists. And then you do this well-defined thing. You integrate out n minus 1 of the electrons, and then pretend you know the reference, right? To some approximation, right? So I guess I have a version of the why has it persisted to talk about measuring orbitals rather than, in other words, is it because of the phase? Do you know what I mean?
You mean why is it a controversy? I don't think it's.
No,
I think it is.
I mean, is it useful to stick with thinking about orbitals because you do measure a phase difference, right?
Yeah.
I mean, you measure a thing that has nodes in it.
Yes.
Right?
Yes.
And then you, from your tomographic reconstruction, you can say that there's a phase jump across there, right? And that seems to fit very well with the orbital picture. So I guess my question is, how do I think about that phase jump in the Dyson orbital? What meaning does it have?
You're thinking about the phase jump between one
Yeah,
side here,
yeah.
one side and the other side?
Yeah.
Well, I would have thought that just comes out of the Dyson orbital, the difference between one and the other. I mean, I've never done the calculations.
Well, I think the simple way to make sense of it is just to think of the single configuration approximation. Because in that case, the Dyson orbital is the HOMO. But of course, the Dyson orbital for the exact wave functions is not just simply the HOMO. So I think
But it would have that same phase relation.
the exact one I don't know, but in the approximation of the single configuration, it would just be the HOMO. Yeah.
I'll go ahead. Oh, we've got one more.
Can you give a clean definition of what a Dyson orbiter is? Because I've never heard of it.
Well, again, I'm not a theorist, I'm an experimentalist, so these guys will give you a better definition than I will. So they can correct me if I'm wrong. I think of it as the n electron wave function minus the n minus 1.
But then it's different terms.
The difference between the two.
How can we
Project out to n minus 1. Pardon?
How can we take the difference between two wave functions that live in different units?
How do you do it? How do you do it experimentally? I think that's the way. How do you do it theoretically? I'll point to the people in the back of the room who will
I will
probably.
write it on the blackboard.
Okay, there. I got the right person. He's got the right people here.
If the marker works, yesterday they worked, so it's this thing here. So we have an n electron wave function and an n minus 1 electron wave function. And this symbol here means integrating out n minus 1 electron. So once you have done that, you have the Dyson, which is the 1 electron. And if you arrange the Attosecond, this is represented by a single state determinant. You remove the valence orbital, and this is represented by, in the same unrelaxed Attosecond, by this all the other same orbitals. So this would just give you, in that case, in Attosecond, this would give you unrelaxed Attosecond, so to say, it would give you the HOMO.
So, very nice is a beautiful description, definition. I mean, it's clear that you have the experimental data, but the interpretation, what you're measuring in terms of electron wave function is based on some theoretical approximation, as Brett and others have said. So it's very linked to the theoretical formulation that you put into your experiment.
Yeah, I think may I come with one comment?
Of course.
I think this is
I may only have
for
to
me.
talk about
I think I don't know. I mean, now for the students, you see, now this is really elevating people or animating people in discussion. This is very great, and this is why this paper, this work, is a key work to know about. Because it's been extremely influential, and if you stay in this business, you will hear about this from time to time in your career. here. So you won't have to study this paper, and you have to think about what is wrong and what is not wrong, and if there's something wrong, and make your own opinion. And I think all of us more senior guys have our opinion, and you can tell you about that also after this talk.
One more, and then I'm going to go ahead. Also, I've got nothing more. We'll have to stop right here.
Okay, so let's say that Dyson orbital is, so I agree with the mathematical definition, but presumably the Dyson orbitals constitute an infinite Hilbert space. And when you measure it, you have only finite number of measurements. So every time you measure it, you collect the wave function of Dyson orbitals. Then how do you reconstruct Dyson orbitals?
Well, I would not say we started out to reconstruct a Dyson orbital. We do a tomographic reconstruction from the data I showed you. So we know nothing about, when we did this, a bunch of physicists, we weren't really into Dyson orbitals, I must say. We just saw it almost in a single electron behavior. But of course, immediately confronted with this issue, what did you really measure? So we did tomographic imaging. It just uses tomography. You saw the data. You saw the arguments, even the approximations we made. I've discussed, and they've been filled in since then. But I've discussed the approximations that are in the paper. So we knew nothing about Dyson orbitals, nor did we have that interpretation. I think by the time the paper, we did the interpretation in the paper. But that's just words you put on top of the tomography. Okay.
Can you do this for hydrogen atom, something you have?
Excuse me?
Can you do this for hydrogen atom, something you cannot?
Well, I couldn't turn a hydrogen atom around, so but of course I could see a spectrum, and maybe I could. So I can't do it. I can't do a tomography. We started out. Let me try to tell you what we started out to do. But actually, maybe I wanted to stop and make a statement in between. So I think I wanted to make a comment. So I thought that it's interesting to think about the relation that's been done here in high harmonic spectroscopy with photoelectron spectroscopy. In photoelectron spectroscopy, you bring in a beam, let's say an XUV beam, and you photoionize, creating an electron in the continuum. It's a photoelectron replica with encoded molecular information in it. And it's, anyway, it's of the XUV pulse. So the information on the molecule is encoded in it. In high harmonic spectroscopy, we do just the opposite. We bring an electron back again. We make a transition moment back to the ground state, an inverse process, and we make a photon replica with encoded molecular information in it of the recollision electron wave packet. So these are very similar processes, just one going one way, one going the other way. Now, of course, to say that they're similar, there's also the tunneling and propagation, but you might say both of these are kind of boring processes. And so the only interesting process in this regard is the returning electron. So there's a deep connection between the two. If you want to look at the differences, high harmonic spectroscopy measures photons, not electrons. Phase matching, not space charge, gives you the limit to how many charges you can have or how many molecules or atoms there can be there. In photoelectron spectroscopy, you get one or two, and the electrons start to repel each other. We heard that in the diffraction work. Here you can have 10 to the 5, 10 to the 6, 10 to the 7, 10 to the 8 photons, and it's okay. Electron exists on the continuum for only a short time. High harmonic spectroscopy is highly multiplexed. Multiple frequencies are produced simultaneously. It would take you forever to do the similar experiment by photoelectron. It can borrow all of the processes and the power of coherent optics. And we're actually using it here because we're putting many atoms together coherently, as if we were doing the experiment on the planet. And optical methods can remove a great deal of space-time averaging in here. I didn't show you that, nor have I made the case on it. However, there's a large field present in high harmonic spectroscopy. That said, what you're competing with, which is some sort of photoelectron, a femtosecond experiments often are relatively strong fields also. So, because when you have a short pulse and you want to do something, you need high intensity because there just aren't many photons. So we're not that far above as a whale-like experiment. Energy conservation can't identify final states as you can in high harmonic spectroscopy. And only weakly bound orbitals are visible, and maybe we have. So those are differences, and I thought it was worthwhile stating them. And let you think about the connection between what we're learning here and what this whole field of photoelectron spectroscopy is. I'm going to go on to chemical dynamics, and I suspect I won't have time for solids. You give me guidance and how to go. Okay, so I think it's natural to go on and say, can we do something in dynamics? Our vision when we started out was right after tomography, and we said, okay, let's see if we can do a movie. We can make a tomographic movie. By the time we got all the data to do it, and we have beautiful data everywhere, we gave up on the idea because of multiple orbitals, and as molecules move around over potential surfaces, orbitals are coming together, and we thought we couldn't keep track of what orbitals were where and what was contributing. So we didn't do it, but we made, I think, beautiful progress, and it's a direction for it first. So let me first start out with the problems. A couple of you brought it up to me in the first place. We said, let's take bromine. It's a simple molecule. So even physicists like us, like me, can understand bromine. Let's do the easiest thing we can. Let's take bromine and photoexcite it to the excited state. And we will choose the state that just directly dissociates into a fragment. So this is going to be the most boring chemistry you can imagine. The molecule just comes apart. But immediately you have a problem. Immediately you know that you can't excite very much from the ground state to the excited state with a short pulse. Again, it's the issue that as you make the pulse shorter and shorter and shorter, its intensity grows and grows and grows. And pretty soon you have no photons unless you get the intensity higher than you would like. And so in order to control the excitation so it goes to where you want and not just somewhere up there into the sky, you have to keep the intensity in bounds. So in this experiment, we started out by doing some, just checking out to see how much we can put and still know where the population went. So 10% is the maximum. So we excite 10%. So how do you possibly identify the signal from these few dissociating molecules in the presence of a strong field against all other possibilities, ionizing, for example, from the ground state or something like that? So photochemistry has always dealt with this problem, or in solids, all short pulse experiments have always had to deal with this problem. And they almost always use something to do with resonance, some way to do it. But here we lose it because we're making harmonics or a continuum. Harmonics are harmonics, so there's no frequency information on the level of the state. And if it's an attosecond pulse, it's a continuum. It's even worse. So there's the experiment again, put in potential curves, potential energy versus separation. We photoexcite, the molecule begins to separate. When we think we want to look at it, we come on with an intense pulse and we ionize it to the ion and look at the high harmonics. So we look at the high harmonics created, so we bring out the electrons back. We don't ionize it, we do it. What will be important is to think about the phase. Remember that the phase the electron accumulates after it leaves the atom and before it comes back again, during the time its trajectory, is the action integrated along the path it takes, plus the difference in the ionization potential, or the ionization potential. So the clock starts ticking from the ionization potential. If your clock is at 0, the clock is ticking here, and the clock is ticking here. If there's population ionized from both here and here simultaneously, they both will have a ticking clock, but the ticking clock for the ground state, the level from which you took the electron will be different, and that difference is the delta phase, delta ionization potential between the excited and ground state. And that builds up significantly For the molecule like bromine, it's 2 to 3 eV. And the time birth to recollision varies on the order of femtoseconds. And so the phase accumulated is a few radians. That's important. That's a significant amount of phase. So when we came to do the experiment, here's what we see. A pump pulse at time t equals 0, and the probe pulse at some time, shown there, time delay in picoseconds. And here we see harmonic 13, 15, 17, 19, 21, and 23. And there's the time dependence. You can see the harmonic signal fell, and it fell sometimes almost by a factor of 2. Now that's amazing at first glance, because we put levels in the high state. You might have increased the ionization probability. But we only put 10% at most in the excited state. So how could we get such a big modulation? Of course, it's that phase I described to you before. The electron from the excited state accumulates phase. The electron from the ground state accumulates more phase, and we have the same frequency but different phase. So that's the blue ones. The red are the even harmonics, and they're caused by the excitation pulse. And so that's really a clear marker of the overlap. There is a time when the excitation pulse and the ionization pulse are simultaneously present, and they lead to even harmonics. But it's only modulating the electron in the continuum. So the seeming disadvantage of having a potential for ionizing from both has gone away, because we can use the ground state as a reference and do a Homodyne detection system. So that's probably potentially possible in any of these short pulse and attosecond-like experiments. You ionize from a couple of things, and if they're coherently related, this is a local oscillator on which to reference. However, we have amplitude and phase mixed in this experiment, and can we get rid of it? In order to get rid of it, we go back to what I talked about last lecture. I talked about trying to bring in some of the techniques from ordinary perturbative measurements, and in this case, transient absorption spectroscopy. Or transient, not absorption, but transient grading spectroscopy. So we said, let's bring our excitation pulse in at 2 different angles. So the excitation then is in a, well, you can see it if you're close enough to the front. I don't know if you can, but illustrated here is the grading that's caused by the crossing of the excitation beam doing the exciting of the molecules. In some places, we have constructive interference and the molecule dissociates, only 10% of course. And in other places, we have destructive interference and no molecules dissociated. So we made a pattern of dissociating and non-dissociating molecules. So that's our pump pulse, t equals 0. And we come now with our probe pulse, which is going to generate the harmonics. And we should see the harmonics diffracted. If you think about the diffracted radiation, which is illustrated here, I'll show you in the next view graph, the amplitude and phase contribute differently to the 0 and first order signal. And so for every frequency, we have a 0 and first order signal. We have 2 measurements and 2 unknowns, amplitude and phase, 0 and first order. So we have amplitude and phase information simultaneously available to us. It becomes a fully coherent spectroscopy at this point. Okay, so here is the results. I thought I had the diffraction, but you can see this is really directly out of the experiment. Not presented for you to see well, but I think you can see that there's diffraction, even in this poor image there. So this gives you then access to the amplitude of the transition moment and the phase difference between the transition moments. The amplitude of the transition moment from the excited state as a function of time relative to the fixed ground state, just to make it clear. And also the phase of the transition moment as a function of time minus the phase of the ground state transition moment. So that's what we have available to us. When you look at this figure, there's a number of very interesting things that you immediately see. You see that in all cases, for the amplitude of the transition moment, there's a rapid fall and then a rise, a rapid fall and then a rise. And you can look at that by scaling them all to the same scale as they're shown in that inset or shown in this inset. And you will see that each harmonic has a different minimum time delay, progressing harmonic to harmonic to harmonic to harmonic. The highest harmonic is the one that's in closest. The lowest harmonic is the one that's at later time delay, in all cases. I'll show you why that is in a moment, and then but I want to also comment on a second thing. There's not so much interesting in the phase here, so I'm not going to comment too much on the phase as a function of time. But there's something kind of interesting, and you probably saw it immediately here. On the second of these, what's the difference? It's illustrated here. The bromine molecule that started out as one molecule and photodissociates either perpendicular to the direction of the electron recollision, or it dissociates parallel to the direction of the electron recollision. We can choose that by the polarization of the excitation pulse. It's a perpendicular transition. So it's not quite as clean as I stated, but it's approximately as I stated. So you see immediately here the disruption of the amplitude of the transition moment in this case. You can see the amplitude of the transmission moment is very well behaved here, and you can see that it has an abrupt change here in all harmonics, and you can see that it's sort of abrupt. It says this very low value where it seems to be distorted. It's a small transition moment, smaller than it would otherwise be. In that case. So what's the cause of that? That's easy to deal with, and I want to talk about that first. So the electron could leave, as the molecule is now dissociated into two components, the bromine plus a bromine atom. It could leave from this atom, go out that way, but it sees something in its way. It's disrupted, and therefore it will not come back and recombine as well here. Of course, it could leave here and come back. Of course, it doesn't mean all signals are destroyed, but it's the phase of the electron is disrupted, at least to a certain extent. And so the emission of the harmonics are suppressed somewhat for that reason. So that's the first thing I wanted to comment. Now I want to go back to the second part and show you the second part. When the ionization occurs from a dissociating molecule, the dissociating molecule goes through different separations as a function of time. And as it goes to different separations, it will get to a place where there's a wavelength and a half, or two wavelengths, or three wavelengths between the two atoms that are there. And so there's a potential for destructive interference when this occurs. Radiation from one and radiation from another atom are out of phase. And we should see that, and we do see that in the decrease in the signal. If that is the case, then the wavelength for longer wavelength light is a longer wavelength electron. And so we should require the atoms to be more separated for the minimum, for the destructive interference to occur in the case of the longer wavelength electron. So in other words, the photon is giving us information about the electron that's doing the real experiment here, and it's telling us where it went, telling us about it. We can calculate the dissociating atom and calculate where the wave packet is as a function of time. And that calculation is shown here on the line, and the harmonic minima are plotted here relative to that line. You can see that it fits well. This, I believe, is pump probe delay. So longer delay, longer wavelength, as I said before, because the atoms are more separated. And so we're essentially doing an interferometry on the molecule, an electron interferometry, the distance between the two atoms in the molecule. Okay, so that's the second thing I wanted to talk about. That's just the second thing I wanted to talk about. So we have a fully coherent spectroscopy. And since then, we've extended it further. We now measure the amplitude and phase of the ground state of the molecule as a function of angle, as a function of angle. And so we have now everything referenced to a one fixed state of just one fixed atom. And so we have all information, amplitude and phase. And of course, this is where we wanted to get to do a tomographic movie, but there are many states involved, and we didn't even try. So, but we have now all coherent information. I think it's almost full information that you can get on this kind of a process. So I think this is a very beautiful kind of spectroscopy. We've taken it to a triatomic molecule, NO2, and looked at a molecule going through a conical intersection, but then that's more chemistry oriented, and I think it's not appropriate. Do you want me to go on? Or do you want me to stop?
10 minutes or so, would it work?
Okay, so I want to end with solids. The issues in solids have come up before. Not really directly in solids, but indirectly in solids. And what happens about the electron? And to a certain extent, I left with something like an issue to solids. If the bromine atom, as they start to come apart, if the electron comes up and hits another bromine atom until it drifts too far away, what happens in a solid where I got lots of atoms around? I guess there's no chance you would think of a recollision process in a solid. And if you'd asked me, I would have said so. That's what I would have said. There's been always a set of people in solid state physics influenced by these ideas, but I personally never took them seriously. So I never looked at it very much. However, when you think about it, we take a great deal of the issues that we deal here, we share with solid state physics. Caldestrated gases and condensed phases in the same thing. So tunneling is still used to describe dielectric breakdown in laser machining with IR pulses. It really is. So maybe we should go back and reconsider a little bit. So before I do that, then I want to just translate what we've been hearing many times here about electrons going out and recolliding, but put it in solid state language. So this is the atomic case still, but just solid state words superimposed on it. So tunneling creates an electron and a hole, makes a jump across the band gap, shall I say, across the ionization potential, the band gap, leaving a hole or an ion, which will move by F equals ma. Its momentum will be the same as that of the electron, F equals ma, right? So there's no reason the momentum, and it will move in momentum space, but its mass is high, and so its energy is fixed. So it'll be a horizontal line in first order in momentum space. The electron, of course, also moves. It moves in a parabolic band. It moves in a parabolic band, and it comes around, and it goes along, as we've seen, and it finds itself in physical space. But of course, it wasn't at the same energy as when it made the transition, or there would be no harmonics. So it finds itself in physical space in the same place, but in momentum space it's somewhere else, and it makes a transition from one band to the other. That's exactly what we've been talking about in solid state language. Okay? Actually, if you go back and you look at the atomic literature, you will see that there's really two kinds of harmonics that are created, only one of which we talk about here and everywhere else. But there's a second kind as well. You can think about it. When you make a transition here, you start and you create a current that's now going to flow in the conduction band. And every half cycle, that current has a jump in it, because the number of electrons are jumping every half cycle as the electron tunnels. So the current, which is the charge times the number of electrons as a function of time, times the velocity as a function of time, has a higher harmonic, not very high, component because of the number of electrons or the time dependence of tunneling. So as we build up the population. So this is a single band term, although that is all of the nonlinearity is here, although it's caused by transition from a two-band. And this is an intrinsically two-band term. The dipole is between the two bands. in solid state language. So in 2011, Gamir and al. So that's Shembu Gamir, you may know him. He's partly from the community of high harmonics. He worked with Zhengyu Cheng for a while. I think he did his PhD with Zhengyu Cheng. And he was working with David Rees, and so David Rees and Shembu Gamir in Ludamoro's lab did an experiment looking at 3.5 micron lights interacting with zinc oxide. Zinc oxide is a large bandgap semiconductor, 3.5 eV bandgap, and they found high harmonics that are generated. Harmonics up to harmonic number 29, I believe, of 3.5 micron light. It was an amazing result. As I said, I was very surprised. And so we decided, after a long delay, to take a look at it and try to work on it. So I began working, or a student of mine really, Giulio Gamba, began working with Thomas Brabitz, somebody who was in the early days in this field quite a bit, and looked at zinc oxide in a two-band model. A conduction band and a valence band, just like I drew for you before, as closely resembling zinc oxide as possible, 1D, 2D, and eventually 3D model, looking at the processes of emission and separating the harmonic generation in the two ways I described to you before, a one-band model and a two-band model. In a solid state sense, a one-band model is different than in a gas. In a gas, I said, there's the constant jumping of population from one band to the other, leading to a step-like behavior in a current. In a solid, the current is also modulated by the structure of the band. As the electron moves not through a parabolic band, but through a band with a shape, its acceleration is unusual in this sign of negative. So it has harmonic content. And in fact, if it gets to the edge of the band, it can jump, and that's Bloch oscillations. Although it's not clear that these experiments got to Bloch oscillation. But that's the interpretation placed on the Bloch oscillations. So here's the results of the calculations for two different cases, no dephasing and dephasing of 4 femtoseconds, which I think is relatively realistic for the solid, especially giving energetic electrons. Shown here in blue are the results of a two-band contribution. You can read in that, or at least at this point, I will encourage you to read it, and I'll show you in a minute that it's really true. But this is a recombination-like process coming back again. And here's the results from the one-band contribution. Both, of course, create high harmonics, but both create them at a different magnitude. You may say that doesn't look like so much, but you have to notice that that's 4 orders of magnitude up to the side. So the differences are about 4 orders of magnitude. So we knew experimentally, of course, that the harmonics are well-defined, and here they're not so well-defined, so dephasing, we put in dephasing to get that realistic aspect. And I think it's... So we looked at a couple of things. Since this is done by somebody from our community, it was natural to put gated Fourier transforms and actually place it also in a Levenshtein-like model formulation, which you can, but here's a gated Fourier transform of the emission, function of time, and the harmonic number. And doesn't it look a bit like what we've been talking about before? It's got a trajectory like, or starts at low frequency and moves to high frequency. Of course, it's not quite the same, but the motion of the electron and structures of bands are not quite the same. And so that's the emission. And here's what we calculate for what was measured by Gamir and et al. Harmonic field strength here as a function of harmonic cutoff, and we see the scaling with the electric field, just like was seen in the experiment. Under motive scaling, we see a square of the electric field with the intensity in gas phase harmonics and solid harmonics. Gamir and al. showed that it was electric field, and we see electric field as well. The region I can describe. Yes?
So what are the axes of that blue figure?
This one is time. I didn't show it here. I cut it out of another one because we got a set of intensities, and because of the block reflections, they're harder to interpret, and I didn't want to make this complicated. So this is time. There's a half cycle from there to there. Well, I think you can see that that would be there. Yeah, it's from there to there. Yes, I'm cycle of the driving field, which is 3.5 microns in this case. I have right offhand, I don't know what it is, be a few femtoseconds. And this is energy going up to the cutoff, and the field strength is up there at the top. All I wanted to show was the trajectory-like or the chirp-like behavior that you know from gas harmonics. So this is coming out of the model. We wanted to set up an experiment to look at what could be done. So, well, again, you've heard in a number of talks about a class of experiments, these that can help you label trajectories. We do a lot of it in Ottawa, and I can't remember who, somebody else mentioned using it in an ionization experiment. I'm trying to remember who it was. In any case, so we said, let's take a fundamental and second harmonic. You know how to think about these things as interferometers. If the pulse is making a harmonic, you know that the harmonics come from an interference of, so it's basically an interferometer too. One going out one way, one going out the other way, and they come in, remember, the opposite way. That gives you the odd harmonics that we're used to. And here's, we see odd harmonics here. If we put a second harmonic on simultaneously, we change the trajectory a little bit, lengthening one arm and shortening the other, breaking the symmetry, leading to even harmonic generation. We need almost no second harmonic in order to do it. I'm going to show you 10 to the minus 5 is required in this experiment. 10 to the minus 5 is fundamental. This is incredibly weak. So it's breaking the symmetry. It's like having an interferometer and changing the symmetry, and the radiation goes out one arm or the other arm of an interferometer. You can say that we're biasing the experiment towards a direction or a perspective, but we're really not. Anything you look at will break the symmetry by putting in even harmonics. If it's block oscillation or anything. I have a curve to show that, but I do that. So here's the result of such a case. Harmonic numbers shown here, up to the limits in our case in our spectrograph were cut off. Here's the phase delay between the fundamental and second harmonic. Odd harmonics, deeply saturated. Even harmonics modulated, as you see, on and off, on and off, on and off. And there's the odd harmonics, and they track up to the 18th harmonic. And what's important in order to look at this is to see what phase of the harmonic gives you the maximum asymmetry. And that phase fit around that trajectory leading to that harmonic optimally. So you can see that the phase of the harmonic gives the maximum asymmetry is shown here in the purple. It's different than a flat face across. The experimental data is here. The comparison with the model is shown here as well. And so it's consistent completely with a recollision process. So I put this earlier, the paper was published in Nature a little while longer. If I have a few more minutes, I don't know.
5 minutes.
5 minutes, I certainly will be done in 5 minutes.
Okay.
The only thing I wanted to say was, I said that you can do unusual things in molecules. Tomographic imaging was one. And I think this kind of strange nonlinearity, we can do other unusual things. And in solids, we can also do something unusual. So I want to end up with that. So is it possible to do something analogous to tomography inside a solid? Now there's a number of things you can think of analogous to tomography. You might try to do a tomographic image of an exciton. And I think that's a very exciting thing, and it might be possible. However, what we decided to look at is, could we reconstruct the band differences, the band structure of a solid? So let me make the argument that maybe one can. What we need to do is measure the energy, that's reported in the harmonic number, and we have to know something about the momentum of the electron that makes the transition between one and the other. But we can know the momentum of the electron from the omega-2 omega experiments. We have this information sitting there, and we can deconvolve them to tell you about the momentum. So we have momentum and energy measurement and information on the semiconductor in question. So this is an illustration. You make a transition, it goes throughout, it finds itself in space, and as long as we know where the K is, and we measure the energy, then we can reconstruct the band structure. So that's just stating basically what I say in words, and I have almost no time. So far our experimental data only goes up to harmonic 16 or 18, and we don't have enough data to fully look at a band structure, which we have to go to 30 eV. What we can only do so far experimentally is identify between a set of potential bands what was contributing to the harmonics. And we find the low mass band is what's important, but that's what we sort of knew in the first place. So what we did differently was we said, okay, we have the two-band model. Let's just solve it numerically. Let's get the experimental data. Let's make this up theoretically. There it is. Let's throw away all information on the band, but just take this as experimental data and reconstruct the band from just the information, no information except the made-up experimental data. So the target band is over here in the middle. And we did not put it in a set of parameterized bands. We did not allow it to be in. And we searched for the best we could out of some like 500 or 600 parameterized bands. And we find the two closest ones. And that's the only ones we got. And that's just published in the PRL. So we believe we can reconstruct from purely optical techniques the band structure of the solid. Now, nobody cares about zinc oxide. Nobody cares about silicon. They know it. So it's not interesting. But it may be interesting in high-pressure materials where you can't get photoelectrons out. It may be interesting in rapidly changing materials where the band structure is changing because of other processes that you're doing to the material. But we think that there's now an all-optical method to look at the band structure of semiconductors, at least large band semiconductors. So let me just finish off then. So we find very similar results in silicon and other semiconductors. I forgot to say that the perturbing field that we need in order to make this noticeable to omega is 10 to the minus 5. This is almost no field at all. It could be applied with a DC field. In fact, we can now measure fields inside semiconductors. We can measure terahertz this way. You need almost no field in order to modify the harmonics, high harmonic signal. Solids provide a medium for attosecond devices, I think. Harmonics are sensitive to very small fields, even fields found in ordinary electronics. And so we should be able to watch ordinary electronics switch, should it be interesting. Even in comprehensive images of a surface using these diffractive techniques that we heard from Margaret yesterday. High harmonics are very tolerant to electronic dephasing, and it's possible to apply tomography to solids to get band structure and maybe to look at wave functions of orbital impurities. And I think liquid phase, maybe, and large molecule is also in play for this as a possible diagnostic. Of course, it's trivial to put almost anything in front of the laser beam and see if you get harmonics, and we get harmonics from almost everything. And that's too simple, but we get it from graphene harmonics. It's amazing. I would never have thought we would. We get it from monolayers of graphene, and we get it from stretched rubber gloves, right? So we get harmonics from such things. Let me just end my part. I think that this is a dramatic and really exciting area. We extend 50 years tradition of ultra-fast science by pushing the duration of pulses down by 2 orders of magnitude. That's what we've done in this Attosecond community. We've extended 50-year tradition of nonlinear optics. We open a whole new direction in gases and now beyond. This is strong field nonlinear optics, so it can be quantitative and it can really work. It can allow us to do new kinds of diagnostics that were never possible before. I think we build a 100-year tradition of X-ray science. We integrate X-rays and lasers. You've heard about this everywhere here, how the integration is occurring. And it's got to be important, it seems to me. Thereby, we extend the spectral reach of laser spectroscopy up into the region where it's been simply before only available in big machines. And we influence, but we don't have nearly such influence, on the tradition of collision science, offering in those areas where collisions can be driven by lasers, but they could be large range of areas. We open the possibility of time resolution. So I think it's we have the potential for very huge impact in science generally. Okay, thank you very much. It's been great. And there's the group that does all the work.
Thank you so much, Paul.
But I'm in Tucson, or down in Tucson.
Enjoying the summer.
Enjoying the warmth. Yes.
So we are kind of running a bit late, but,
Yeah,
but
sorry.
if there are some urgent questions, we should still take them.
Hours.
Huh?
It's not working.
But you have an urgent question.
Oh, not super urgent.
Go ahead.
Okay, so would the sync of sight the large band gap critical, or can you do smaller band gap semiconductors?
Well, we looked at we don't know. So, maybe I could talk a long time, and so I was trying to think of this. We've used always 3.5 micron light, so I don't know how far down we can go. But we can do silicon. And silicon has got a much smaller band gap, but for this it's the direct band up that counts, so it's about 2 eV in silicon. So you make a jump across the direct band gap. So we can do silicon. We have looked at gallium arsenide, but there's not so much interesting there. It's not clear. I would say that the issue of harmonics, to give you maybe I should say it to everybody, the issue of harmonics from solids will be more complicated than it is from gas. From solids, this is, I think, clearly recollision, large bandgap semiconductors. There's work done in SiO2, a very dielectric, and I think there's no chance that's recollision. This is a different process, probably different than almost anything we've thought about very much. It looks like the electron is highly localized and the processes are quite different. Maybe it's almost two-level harmonics. We've been doing work on this some in Ottawa, trying to understand the breakdown in large bandgap dielectrics, and there's a lot of work done in this. And there's work in terahertz on this, and it seems also to be very different. We would say dephasing would kill recollision with terahertz, and that's not inconsistent with what's seen in terahertz experiments. So solids will be more nuanced and a broader range of strong field processes, but high harmonics seem characteristic of a number of strong field interaction. And so there are at least 3 mechanisms probably at play, and maybe more. But there is a window, and maybe a reasonably interesting and large window open for recollision. I think mostly it's important for diagnostics. That's why I like to start with the bandgap. I like to look for diagnostics. I better stop.
This is great. You're still here this afternoon, right?
I'm staying until Monday. I leave Monday morning.
Oh, yeah. So you guys, you should absolutely make sure that he doesn't get too relaxed.
Okay, thank you. Thank you, everybody. It's been great.